Hello. Oh, yes. We welcome you back to PSSB, Physical Sciences Silver Bullet. Okay, now we are looking at this question. The question comes from Electrochemistry. It says, consider the standard electrochemical cell represented by half cells below. So we have these two half cells. One is this one, and also this one. And the question says, write half reaction at cathode. So how do you start with this question? Okay, this is one of the series of questions which requires us to use the table of standard reduction potentials. What do we get from the table? We are going to get to know which one is cathode and which one is anode. Now, there are two tables at our disposal. There's table 4A and table 4B. Both of them can be used depending on the tutor. I find table 4B convenient because table 4B happen to have strong reducing agent at the top and the strong oxidizing agent at the bottom. Now, this setup gives us some advantage. What advantage? It gives us our anode to be on the top of the cathode. What advantage does that one give us? Remember, A comes before C in alphabetical order, so we don't have to think. You just know that when you are using table 4B, what you meet first is your anode, and what you meet next is your cathode. So that's the advantage we get from the table. So when you look at these two half cells, what do we notice? We notice that the copper half cell is on the top of this hydrogen peroxide half cell. And what does that mean? It means that copper half cell is the anode and this half cell is the cathode. And what do we know? We know that what happens at anode is oxidation, and what happens at cathode is reduction. So all these problems are being solved by simply using table 4B. So those are the advantages we get from there. So that is that. Now let us look at the two half reactions as we get them from the table 4B. Okay. Now we have the two half reactions as we take them from table for B. This is what you have to remember, that all these reactions which are in the table, they are rated in the reduction manner. Actually, that's the reason why the table is called standard reduction potential. Why they choose reduction is not the question of the point, but all of them are reduction reactions. So they can be referred to as a standard reduction potential. Some people call them standard electrode potential. Okay. Now, let's come back to the question. The question says, write half reaction at cathode. What reaction occurs at cathode? It is reduction. And all the reactions in the table are reduction reactions. So under the circumstance, what do? You pick this reaction and it happens to be your reaction. The only thing you do is that you remove the reversible sign and put it in one direction. Let's do that. Okay, that is that. So the half reaction at cathode is this one. Let's go to the next question. Yes, then comes this question. It says, write oxidation half reaction. We have to recall that oxidation occurs at anode, and which half cells anode is copper. You have to also to remember that whatever is written here is reduction. So how does it fit here? The reverse of this one is going to be the reaction here. So we are going to have copper being oxidized to copper ions plus 2 electrons. You must not forget and put the double arrow. It's supposed to be single arrow. Okay, that is that. So then comes another question. It says, write the net reaction. How is it supposed to be? Okay, literally, net reaction is going to be our reduction reaction plus our oxidation reaction, combining them together, cancelling out the electrons. What remains behind is the net reaction. Thank you. So this is what we have. So after that, you cancel these electrons out, and what remains behind is the net reaction. So that is that. So this happens to be our net reaction. We advise learners that after getting your net, you cancel out with this one, because through not being careful, somebody might think your net is this one. So the working, it's advisable that you cross it out and you remain with only your net. Thank you. So let us go to the next question. Okay. Then comes this question, 3.1.4. It says that write the cell notation for the cell. Okay, how do you construct this one? Actually, you have to remember that the cell notation depicts the setup of the cell without the diagram. Okay? And the arrangement is a standard, that what is on the left is supposed to be the anode, and what is on the right is supposed to be the cathode. So what do we have for the anode? You come and check. Remember, our anode is this one, the oxidation reaction. So we write it Cu solid. This one, remember this is a solid. Now we are going to ions. This bar represents phase change. So you are moving from solid to aqueous medium. So that's why you put that bar. Then from here, this half cell has been represented. What comes next is the salt bridge. After salt bridge, you bring your cathode. And what does it say? We have oxygen gas. From oxygen gas, we are going to hydrogen ions. So you put a bar and hydrogen ions. Why? Because this is a gas and you're moving to another phase, which is aqueous. Then from there, aqueous, you are going to hydrogen peroxide, which is also aqueous. So you put it there. Then after that, you have to remember that this aqueous medium cannot be the electrode. Remember, at the ends of the cell notation, we must have the electrodes. So if you recall, our electrode was put here this time around, is platinum, and you are coming from aqueous medium going to solid, so you put a bar and put platinum. So what we have there is the cell notation of this cell. Okay, then comes the next question. It says, calculate the cell potential of the cell. Okay, how do you approach this one? We are going to use the equation. It says that E naught cell, naught means standard, conditions are applying. E naught cell is equal to E naught cathode minus E naught anode. Okay, from there you go to your table of standard electrode potentials and get those values. Okay, after that, then comes another question. Explain why the reading on the voltmeter becomes 0 after some times. Why does it become 0? Okay, you have to know that we are dealing with a cell, and the only time when the cell is providing potential difference is when the reaction is proceeding in the forward direction. But once the reaction reaches equilibrium, it means that the cell potential is 0. There's no potential difference. So what's the answer to this one? The reading becomes 0 because the cell has reached equilibrium. Okay. So that's that. The cell has reached equilibrium. So we look at the next question. So the question comes, it says, how will the cell potential change when concentration of copper ions is increased? So how do we answer this question? To answer this question, we need to know the half reaction at copper. We have to remember that we found our copper to be the anode, and the anode undergoes oxidation. So the half reaction is a solid being oxidized to copper ions. Okay, that's the half reaction. So to answer this question, you need to borrow knowledge from equilibrium. This is what we are talking about here. And we are increasing the concentration of this one, which is a product. How will this, if it was equilibrium, how will it behave? The behavior will be to favor reverse reaction. And you have to know that in this case, any situation which favors reverse reaction decreases cell potential. And the any situation which favors forward direction increases cell potential. So because reverse is favored here, cell potential will decrease. So that is that. Cell potential will decrease. Then we come to the next question. Okay. Then comes this question 3.22. It says, how will the cell potential change when distilled water is added to the copper half cell? Okay. Yeah, like we said before, to answer this question, you need the half reaction. And you have to recall that the half reaction at copper half cell is oxidation. Okay. And what is the impact of adding distilled water? The impact is reduction in concentration of copper ions. And you have to remember, when you borrow knowledge from equilibrium, from Lechetaria, withdrawal of copper ions favors forward reaction to form them, because according to Lechetaria, the equilibrium does not want to be disturbed. So what do we notice here? Forward is favored, and any condition, any situation which favors forward direction increases cell potential. So what is the answer? Cell potential will increase. So that is that. And with that, we are going to cut this question here. We thank you for your time. If you have not yet subscribed, please do so. The channel is PSSB, Physical Sciences, Silver Bullet, and it's me, Richard. See you next time. Bye.